Welcome to The Explainer. All right, today we're going to tackle a word that, yeah, it sounds a little intimidating, stoichiometry. But trust me, this is the key to all of modern chemistry. You can think of it as the ultimate recipe book for the universe, one that tells you exactly how to measure ingredients you can't even see. So let's just start with the big puzzle, right? I mean, we all know that everything is made of atoms and molecules, but they're impossibly small. You can't see them. So how on earth does a chemist actually work with them? I mean, think about it. You can't just pick one up and put it on a scale. And you definitely can't count them out one by one like you would with marbles. This whole measurement problem, it was the central challenge that chemistry had to solve to even become a modern science. And the solution to this puzzle, it's actually a brilliantly simple and honestly super powerful idea. Chemists basically invented a brand new unit of measurement, and they called it the mole. Okay, so what is a mole? At its heart, it's just a specific quantity. It's the chemist's special counting number. The unit is mole, and this little thing is the key. It's what lets us connect that tiny invisible world of atoms to the world we can actually see and touch in the lab. And when I say it's a specific number, I mean it's a huge number. Mind-bogglingly huge. It's 6.022 times 10 to the 23rd. That's a 6 with 23 zeros after it. We're talking 602 sectillion. And here's the cool part. 1 mole of anything, whether it's carbon atoms, water molecules, you could even have a mole of donuts. It's always going to be that exact same number of items. Really, the best way to wrap your head around it is to think of it like a dozen. You hear dozen, you think 12. No questions asked. Well, a mole is the same idea. It just stands for that ridiculously large number, which has a fancy name, Avogadro's constant. And by using this concept, chemists can finally count atoms in manageable chunks, instead of trying to count them one by one, which is just impossible. But here's where the mole becomes a real superpower. Its real strength is how it connects that invisible world of particles to things we can actually measure in the real world, like mass and volume. It's basically a universal translator for chemists. So let's look at the first connection, which is the most direct one. It's what we were just talking about, linking the mole straight to the actual number of atoms or molecules using that big number, Avogadro's constant. And the math here is beautifully simple. If you know how many moles you have, you just multiply by Avogadro's number, and bam, you know the exact number of particles. And it works the other way too. If you know the particle count, you just divide by that same number to get back to moles. Easy. So, for example, say you want to know how many molecules are in half a mole of carbon dioxide. Well, you just take 0.5 and multiply it by Avogadro's constant. The answer is this staggering number, 3 times 10 to the 23rd molecules. It's really that straightforward. Okay, so that's the link to particles. But this is where it gets really, really useful. How do we take this abstract counting number and connect it to something we can physically measure in a lab, like with a scale? The answer is mass. The magic key here is something called molar mass. And this is awesome because for any element, you can just look it up on the periodic table. It's right there. It's simply the mass in grams of exactly 1 mole of that stuff. And the relationship is, again, super simple. Moles times molar mass gives you the mass in grams, the very thing you can weigh on a scale. This right here, this is where it all clicks into place. Imagine a chemist weighs out, say, 2.4 grams of magnesium. They look at the periodic table, find the molar mass for magnesium is 24 grams per mole. They just divide the mass they measured by that molar mass, and they know they have exactly 0.1 moles. Think about what just happened. They've basically counted the atoms just by weighing a pile of them. How cool is that? All right, there's one more connection we need to talk about, and it's a brilliant shortcut, a little trick that only applies to gases. See, under what chemists call room temperature and pressure, which is pretty much what it sounds like, about 25 degrees Celsius and normal air pressure, something really amazing happens. And this is just fantastic. It turns out that 1 mole of any gas, and I mean any gas, it doesn't matter if it's helium, oxygen, carbon dioxide, whatever, it will always take up the exact same amount of space under those conditions. And that volume is 24 decimeters cubed. So let's put that into practice. If you measure out 2.4 decimeters cubed of CO2 gas, all you have to do is divide by that magic number, 24, and instantly you know you have 0.1 moles. It's a way to count gas molecules with nothing more than a measuring cylinder. It's incredible. Okay, so now we know how to measure our ingredients, right? We can connect moles to mass, to the number of particles, to the volume of a gas. Now we can finally start cooking. And this is where stoichiometry becomes all about following chemical recipes. And, just like when you're baking cookies, you rarely have the perfect amount of everything. You always run out of chocolate chips first, right? Well, in chemistry, the ingredient you run out of first is called the limiting reactant. It's what stops the reaction and determines the absolute maximum amount of product you can make. Everything else is just in excess. Of course, reactions in the real world, they're messy. They're rarely perfect. And that's why chemists are obsessed with something called percentage yield. It's basically a report card for your reaction. It compares how much stuff you actually made versus how much your recipe said you should have made. And this really matters. In industries like pharmaceuticals, a high yield means less waste and lower costs. That's a huge deal. Okay, so let's zoom out and look at the big picture here. All these different ideas, the mole, the limiting reactants, the yield, they all come together to form chemistry's master blueprint. It's the fundamental toolkit for literally changing the world around us. So this is it. This is the essential toolkit for any chemist. You've got the mole, that's your central counting unit. You've got mole ratios, which are basically the recipe from your balanced equation. You know how to find the key ingredient, the limiting reactant. You can figure out how pure your ingredients are and how efficient your reaction was with percentage yield. You can even figure out the simplest ratio of atoms in something. It's the whole blueprint for analyzing and creating, well, anything. And at the end of the day, this is why stoichiometry is so important. It's not just some abstract theory in a textbook. It's the practical, mathematical bridge that connects that invisible world of atoms and molecules with the real, tangible stuff we can see and hold and use every single day. I mean, this is the foundation for everything, for developing new medicines, for creating advanced materials, for finding sustainable energy solutions. It all comes back to this one simple, powerful idea of how to count atoms. Which leaves us with a pretty fascinating final thought, doesn't it? If chemistry is the science of changing matter, what could we create if we could measure and control every single atom perfectly?